All right, so this is our formal lab number 2, where we are discovering viscous drag. And so our question was, how does the viscosity of different fluids affect the velocity and acceleration of a marble flowing through the fluid? And so we use 3 fluids in this lab: syrup, water, and soap. And by changing the fluid that the marble flowed downward through, we were able to determine the value of the viscous force of each fluid on the marble. And when we came to our conclusions, we've realized that the larger the velocity and acceleration, the less viscous the fluid is. So the methods we use for this lab is we use 3 50 milliliter graduated cylinders, and we filled them with either water, soap, or syrup, all to the 50 milliliter line. These cylinders were placed against the wall, and a recording device, a phone, was placed directly in front of the cylinders, and that position of the phone and the position of the cylinders were never changed. The marble was placed on the rim of the graduated cylinders every time, and this allowed for each trial to maintain maximum consistency between each drop. And after each time, the marble was removed from the graduated cylinder using a magnet, and this was clean before each drop to make sure no fluid was contaminated with another fluid. Our force diagrams, the force diagram to the far left is describing the force of gravity being maximum, because this is before the marble actually touched the viscous force, or the viscous force. And as the marble began to accelerate through the fluid, as you can see, the resistive force, opposite of the force of gravity, became greater, almost to the point where they were both equal. And that was when we reached terminal velocity. And that was when there was no longer acceleration.
All right, so based on our observations, we noticed that there was drastic differences in the viscosity between the substances. And we were not able to witness the marble reach terminal velocity in the water, but we did notice that it reached terminal velocity in both the soap and syrup. So for our syrup conclusions, we assume the viscosity of the syrup was around 2000 CPS. And when we plug that into the equation with our velocity of negative 0.29 meters per second, we got a viscous force of 0.071 newtons. And for water, we know the viscosity of water is around 1 CP, depending on the room temperature. And after plugging those values into the viscosity equation, we found that the viscous force on the marble in the water was 0.00015 newtons per meter squared. And for the soap, we found that the viscosity of the soap was around 3000 CPS. And after plugging that into the equation with our velocity of 0.18 meters per second, we got a viscous force of 0.066 newtons per meter squared.
So for our qualitative error, our main sources of errors were like, we needed to make sure that the fluid we were using was 100%, like not at all diluted, so we had no way of knowing that. We also were concerned with whether or not the marble was like fully cleaned, to make sure all of the viscous fluid from the previous test was cleaned off of it. And finally, and probably the most noticeable one, is making sure the marbles were dropped from the same height. When analyzing the data on Tracker, it wasn't super easy to see, but there was a pretty big difference between the placement of some of them before they dropped. So we tried to control a lot of the error by dropping like the marble from, the rim of the cylinder for each trial, but obviously not everything could be controlled. So the standard deviation for the velocity points, like from Tracker, were based on their average velocities from each trial. So for water, the standard deviation was 0.047. For soap, it was 0.005, and for syrup was 0.008. And obviously, we can see that the lower standard deviation is better, so soap had the lowest standard deviation.
All right.